Heat. Learning objectives. Conversion of energy. Sources of heat energy. Effects of heat. Expansion. Temperature. Amount of heat. Change of state. The ability to do work is energy. When a person has the power to do work, we say that he has energy. Similarly, when we do not eat food, we do not feel like working, or if we work, we soon get tired. Then we quit. I don't have enough energy. Here we will study about heat, which is a form of energy that is transferred by a difference in temperature. As heat produces energy, it has the ability to do work. Examples. In steam engine, heat is used to raise steam which turns a turbine. Steam turbine. 2. Hot gases in a hot air balloon, being lighter than the surrounding air, rise up in the air and are used to lift weight. 3. Heat is used to produce mechanical energy. Balloon with hot air lifts weight. 4. An iron, when heated, is used for ironing the wrinkled clothes. A cool iron does not remove the wrinkles. Pressing clothes with iron. Conversion of energy. The law of conservation of energy states that the total energy of an isolated system is constant despite internal changes. Examples. Conversion of heat into other forms of energy. Heat energy is converted into light energy. For example, when charcoal is heated, it emits light. Charcoal heating. 2. Heat energy is converted into mechanical energy. For example, a steam engine pulls a train. Steam engine. 3. Heat energy is converted into sound and light energy. For example, the heat in a firecracker produces both sound and light. Firecracker. Conversion of other forms of energy into heat. The other forms of energy can also be converted into heat energy, such as 1. Friction, mechanical energy, produces heat. For example, the friction between the palms, when rubbed vigorously, produces heat. 2. The striking or collision of two pieces of stone produces heat and fire. Hand rubbing. 2. Chemical energy produces heat. For example, when a candle burns in air, chemical energy within the candle is converted into heat. 3. Electric energy produces heat and light. For example, when we switch on an electric bulb or tube, the electric energy produces heat and light. Stone rubbing. Burning candles. Electric bulb. There are several such examples which demonstrate the conversion of one form of energy into another. Sources of heat energy. There are various sources of heat energy. These include heat energy, sun, fuels, food, electricity, nuclear. Facts. Energy cannot be destroyed, but it can be, and constantly is, converted from one form to another. Effects of heat. When an object is heated, many changes take place. 1. The objects may expand in size upon heating. 2. A substance, on being heated, may change its state. For example, when ice is heated, it changes into water. 3. Heat can accelerate chemical reactions. 4. Heat can even kill. Examples. Boiling of milk and drinking water kills the harmful bacteria present in them. 2. Heat of the sun kills plants in summer, if not watered regularly. 5. When a hen sits on its eggs, it gives gentle and sustained warmth which produces a chicken. 6. Heat helps in cooking. For example, cooking of food, making of chapatis, puris, etc. Heating ice greater than changed into water. Boiling milk. Hen laying eggs. Frying food. Expansion. Most of the substances expand on heating and contract on cooling. This effect of heat to expand substances is called thermal expansion. Let us study thermal expansion in solids, liquids and gases. A. Thermal expansion in solids. The expansion or contraction in solids is too small to be seen easily. Take an iron rod and a copper rod of the same length. Place an iron rod between two wooden blocks. The raised wall of one of the blocks holds one end of the rod firmly in position at its one end. A round pencil is placed under the other end of the rod. Attach a paper pointer to a pencil. Now heat the rod. As the rod expands, it pushes the pencil, which makes the pointer rotate. You notice that the thermal expansion does take place in a solid when it is heated. Take the ring and ball apparatus. Insert the ball in the ring. The ball passes through the ring easily. Now heat the ball over the flame for 10 to 15 minutes. Repeat the step. 2. The ball does not pass through the ring. Allow the ball to cool and repeat the step. Again. 3. The ball passes through the ring again. Solids expand on heating and contract on cooling. Such expansion on heating is frequently used to make some tasks easier. Ball, before heating. Ball, after heating. Examples. When a metallic rim, iron wheel, is to be fitted on a wooden wheel of a bullock cart, the blacksmith always first heats the rim. This heating expands the rim so that it slips easily on the wooden wheel. As the rim cools down, it contracts to its correct size and fits tightly on the wooden wheel. 2. The tight neck of a bottle, pen, etc. when heated gently over a flame and then unscrewed, it opens quickly and easily. 3. A small gap is left in between the joints of a railway track to allow the expansion during summer. 4. The telephone and other wires in between the poles are kept loose to allow their contraction in winter. Similarly, a gap is left at one end of the bridge while laying the girders and the other end is fixed. The girders are kept on rollers to allow expansion during summer. Railway track. Telephone poles. Girders in bridge. B. Thermal expansion of liquids. The expansion in liquids is comparatively more than solids when heated. Let us study it by performing the following activity. Take a round-bottomed flask filled with colored water. Insert a rubber cork fitted with a hollow glass tube, such that little water is visible in the glass tube. Mark the water level. Heat the flask over the flame. The water level rises above the mark. Cool the flask after heating. 2. The water level returns back to the mark. Thus, you can infer that liquids expand on heating and contract on cooling. See thermal expansion of gases. Gases also expands on heating. Let us study it. Take the test tube and fit it in one holed rubber cork with the hollow glass tube. Put a drop or two of ink or colored water in the hollow glass tube. Heat the test tube over the flame. The colored water or ink in the tube rises up. Remove the test tube from the flame. 2. The level of ink or colored water falls down. On heating the test tube, the air in the test tube expands and pushes the colored water up. When the test tube is cooled, the air contracts and the level of the colored water comes down to its original level. Sci facts. If you heat gas and water, the gas expands faster than water. Temperature. The degree of hotness of an object is called its temperature. How to compare the temperature of two objects? We can know the temperature of the object by the following ways. 1. By using our sense of touch. By using our sense of touch, we can compare the temperatures of two objects. But we can do this only if the heat is bearable. For example, we can compare the temperature of hot milk with lukewarm water by touching the tumbler or container containing it. We can decide which one of them is at higher temperature. But, however, we cannot use our sense of touch to find the temperature of boiling water, burning coal, fire, etc. because it is too hot to touch by hand. But, even the bearable temperatures, like body temperature of a man, cannot be known that easily. Thus, our sense of touch helps us to know only the difference in temperatures, but in no case it gives us the idea to what extent it is hot. For this, we need a reliable device. We have got such a device in thermometer. 2. By relying on the fact that substances expand on heating. Examples. A. Measuring temperatures on the basis of expansion of solids. We can compare the temperatures of two substances by bringing them in contact with a metal rod. The substance that produces more expansion in the rod would have a higher temperature. However, this method may not be practical because solids expand so little that we might need another instrument to measure the expansion. B. Measuring temperatures by using the expansion of liquids and gases. It would be more convenient to use liquids and gases for measuring the temperature because the liquids and gases expand much more than solids on heating to the same extent. Temperature scale and thermometer. Temperature is a measure of the amount of heat energy possessed by an object. See our energy module for more on this concept. Because temperature is a relative measurement, scales based on reference points must be used to accurately measure temperature. There are three main scales commonly used in the world today to measure temperature: the Fahrenheit, degree Fahrenheit, scale, the Celsius, degree Celsius, scale, and the Kelvin, K, scale. Each of these scales uses a different set of divisions based on different reference points, as described ahead in detail. A. Celsius scale, THE Celsius temperature scale, degree Celsius, was developed by Anders Celsius in 1742. The 0 point of the Celsius scale is set to the temperature at which water freezes. The number 100 is set to the temperature at which water boils. Celsius set 100 equal divisions, degrees, between the freezing and boiling points. The Celsius scale is the standard scale used around most of the world to measure air temperatures. B. The Fahrenheit scale, suggested by Gabriel Fahrenheit. This scale is usually used in clinical and meteorological purposes. Here, the ice point and the steam point are correspondingly marked as 32 degrees Fahrenheit and 212 degrees Fahrenheit, and the fundamental interval is divided into 180 equal divisions. Each division is called 1 degree Fahrenheit, 1 degree Fahrenheit. C. Absolute scale or Kelvin scale. It is designed by scientist William Thomson, also known as Lord Kelvin. It is used internationally in modern scientific world. In this scale, the ice point is marked 273 K and the steam point 373 K. The fundamental interval is divided into 100 equal divisions, like that in the Celsius scale. Each division is read as 1 degree absolute or 1 Kelvin, 1 K. In fact, Kelvin scale of temperature starts from the temperature corresponding to minus 273 degrees Celsius, taken as a 0 Kelvin. A temperature measurement in any of the three scales can be easily converted to another scale using the simple formulae given below. Celsius to Kelvin, K equals C plus 273.15. Celsius to Fahrenheit, F equals 9 into 5C plus 32. Fahrenheit to Celsius, C equals 5 into 9, F underscore 32. Fahrenheit to Kelvin, K equals 5 into 9, F plus 459.7. Laboratory thermometers. Laboratory thermometers are used to measure temperatures or temperature changes with a high degree of precision. They are made of metal or glass and strengthened through processes such as thermal tempering or annealing. Several types of laboratory thermometers are commonly available. Liquid and glass thermometers are made of sealed glass and contain a fluid, usually mercury or red alcohol, whose volume changes relative to its temperature. Laboratory thermometers measure temperatures in degrees Fahrenheit, F, or degrees Celsius, degrees Celsius. Laboratory thermometer. Clinical thermometer. This thermometer is a short-range thermometer which covers a few degrees on either side of the average temperature of the human body, i.e., 98.4 degrees Fahrenheit. This thermometer is generally used by doctors. A clinical thermometer consists of a thick-walled glass capillary tube of uniform and fine bore. A thin-walled cylindrical bulb is provided at one end of the capillary tube. The capillary tube is sealed at the top. Pure and dry mercury fills the bulb and a part of the tube. The stem is graduated in degrees. Just above the bulb, there is a small constriction in the stem. When the temperature rises, mercury easily passes through this constriction. But the reverse is not true, i.e., when the temperature falls, mercury cannot pass this constriction. The front part of the thermometer is made prismatic in shape. This gives a magnified view of the scale and thread when observed from a suitable angle. A small red or black arrow is marked on the stem at 98.4 degrees Fahrenheit, which is the normal temperature of the human body. Clinical thermometer. Digital thermometer. Digital thermometers are temperature-sensing instruments that are portable, have permanent probes, and a digital display. They are typically battery-powered. Digital thermometers can have many display scale characteristics. These include Fahrenheit display, display range and scale divisions, Celsius or centigrade display, display range and scale divisions. Digital thermometers can display temperature in Fahrenheit or Celsius, or both in a dual-scale thermometer. The display range is the minimum and maximum values of temperature that can be displayed. Digital thermometer. Reading a thermometer. Use standard precautions. Washing hands and wearing gloves if appropriate. Handle the thermometer with care to prevent chipping or breaking. Remove the probe cover and/or wipe the thermometer with a dry tissue from stem to bulb. Do not use an alcohol swab before reading the temperature reading. Hold the thermometer at eye level and parallel to the floor. Position the thermometer so that the solid colored back is away and the numbers and lines are facing the person reading the thermometer. Look for the top edge of the liquid. It may appear gray, red, or another color, depending on the type of thermometer used. If the liquid is not seen, slowly and slightly roll the thermometer between the fingers until the color can be seen. People with poor eyesight may need to magnify the thermometer. A thermometer. When reading a Fahrenheit thermometer, long lines indicate 1 degree. Short lines indicate 0.2 degree. When reading a Celsius thermometer, long lines indicate 1 degree or 0.5 degree. Short lines indicate 0.1 degree. Be careful when reading temperatures between 100 degrees and 101 degrees. Many people mistakenly record or report the tenth of a degree as a whole degree. For example, 100.2 degrees is between 100 and 101, while 102 degrees is between 102 and 103. Reading a thermometer. Amount of heat. The amount of heat can be measured from the change in temperature that it produces. We shall study the relation between the amount of heat and the temperature change in different substances. Take 2 beakers of 250 milliliters. Take 200 milliliters and 100 milliliters of tap water in the beakers. Note the temperature of water in both the beakers. Place beaker A with 200 milliliters of water on a tripod stand over a wire gauze. Heat it over the flame for 5 minutes. Note the rise in temperature of water. Now place beaker B with 100 milliliters of water over the flame. Heat it for 5 minutes and note the rise in temperature of water. The rise in temperature of 100 milliliters of water is almost twice the rise in temperature of 200 milliliters of water. The rise in temperature depends on the amount of water taken. Unit of heat. The rise in temperature depends on the amount of water. From it, we can define the unit of measuring the amount of heat. This unit is called calorie. 1 calorie is that amount of heat which can raise the temperature of 1 gram of water by 1 degree Celsius. Calorie is abbreviated as cal. We also use kilocalorie to measure the amount of heat. 1 kilocalorie equals 1000 calories. Kilocalorie is abbreviated as kcal. Nowadays, the unit of heat energy used is joule. Joule is the accepted international unit of heat and is abbreviated as J. 1 calorie equals 4.184 J. Heat capacity. On supplying 1 calorie of heat or 4.184 J of heat to 1 gram of water, its temperature rises by 1 degree Celsius. Let us find out what would be the rise in temperature if the same amount of heat is applied to 1 gram of vegetable oil or 1 gram of iron. Hence, the heat capacity of a substance is the amount of heat needed to raise its temperature by 1 degree Celsius. The unit of heat capacity is joule per degree Celsius. Water has the highest heat capacity. Activity 14.1. Take 100 gram of water in beaker A and equal weight, 100 gram, of vegetable oil in beaker B. Heat both the beakers over the flame for 5 minutes. Note the temperature before and after heating the liquids. Before noting the temperatures, stir the liquids so that heat is uniform throughout. Compare the rise in temperatures. The temperatures of oil rises much more than the water. The rise in temperature is different in different substances even if the same amount of heat is supplied to it. Specific heat. The specific heat of a substance is the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. The unit of specific heat is J/kg degrees C. Sci facts. In steam engine, heat is used to raise steam which either turns a turbine or forces a piston to move up and down in a cylinder. Change of state. You know that there are 3 states of matter: solid, liquid and gas. One form of matter can be changed into another form. For example, solid, liquid, gas. The temperature at which a substance changes its state from solid to liquid is called its melting point. The temperature at which a substance changes its state from liquid to gas is called its boiling point. Different substances have different melting and boiling points. Melting points: immerse a thermometer in the ice and read the temperature. Keep the beaker on the wire gauze on a tripod stand and heat it with a spirit lamp. Keep reading the temperature. The temperature of ice remains 0 degrees Celsius. When all the ice has melted, only then the temperature starts to rise. Melting point of ice is 0 degrees Celsius. Activity 14.2. Take 100 milliliters of water in a beaker and keep it over the wire gauze on a tripod stand. Heat water over the flame. When water starts boiling, note the temperature of water with a thermometer by dipping its bulb into the water. The temperature rises in the thermometer and becomes constant at 100 degrees Celsius. Thus, the boiling point of water is 100 degrees Celsius. Keywords. Boiling point, the temperature at which a liquid changes its state to gas. Calorie, a unit of heat. Heat, a form of energy. Heat capacity, the amount of heat needed to raise the temperature of a substance by 1 degree Celsius. Joule, the internationally accepted unit of heat. Melting point, the temperature at which a solid changes its state to liquid. Specific heat, The amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Summary. Heat is a form of energy, hence, it has the ability to do work. One form of energy can be changed into another. Substances expand on heating and contract on cooling. Solids show the least expansion while gases show the most. The degree of hotness of an object is called its temperature. A thermometer uses the expansion of the liquid within to measure temperature. 1 calorie is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Heat capacity is the number of joules required to raise the temperature of a substance by 1 degree Celsius. The specific heat of a substance is the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. One form of matter can be converted or changed into another form. The temperature at which a solid changes into liquid is called its melting point, and the temperature at which a liquid changes into gas is called its boiling point.